Hello, my name is Matt Bodwell. I work for EnviroCare. We're becoming Saveco. We're a member of WAM Group. I've been in the industry for about 14 years with EnviroCare for about 4 years now. EnviroCare is a headworks screening and grit removal company primarily. I'm here today to talk about the effect of screen design on capture rate and plant maintenance in both water and wastewater treatment. This presentation is geared around, first of all, a little bit of background information, why we screen, where does debris come from, but then talking about what types of screens are available, including the independent testing results that help standardize a lot of the screening industry. Then get into the hydraulic design of screens, the different types of common screen types, and then have a summary at the end. So diving into it, why do we screen? It sounds simple, you're looking to protect your plant, but really what are we looking to do? First, you've got downstream processes immediately after the headworks. So if you can keep material out of those processes, your clarifiers that start to get bogged down with rags, digesters, what have you, pumps, pump lines, those all are maintenance items. Your sludge quality, if you can improve that, you can improve the class required for discharge, as well as your overall appearance of your final effluent. Those are all great benefits, but the big one is that one at the end, the reduced the amount of money you're spending on the poorly functioning treatment systems. That's really what we're looking at. The better you can protect your processes, the better you can protect the plant by having a good, effective headwork system, the better it's going to be as far as your operation and maintenance cost goes. We're always looking to find ways to decrease costs to run a plant. The very best thing you can do is make it cheaper to run the plant overall by protecting it at the headworks. So where does this debris come from? The stuff that's going to cause you issues downstream. Well, obviously, we're in the wastewater industry. Toilets are one of the most common areas that you're going to get a lot of debris coming down. This is summer of 2020. As we all know, the pandemic started a few months back, and at this point, it feels like a lifetime. A lot of material started getting flushed down during that toilet paper run. A lot of material ended up causing issues with plants. A lot of news articles came out, so obviously toilets are a big concern. But there's a lot of other areas where flow can enter into the plant as well. For example, your kitchen. You've got sinks. They're all draining down into the sewer system. You get a lot of eggshells, coffee grinds, corn, things like that getting down to the plant. Sometimes other things get flushed down. And then, of course, you've got garbage, debris, particularly for a combined sewer system. Anything that ends up for litter on the ground ends up in a sewer system more often than not, and then ends up having to be pulled out by the downstream processes, and particularly your screens. So ultimately, it all ends up down at the plant. You end up with a lot of pictures like these. You can see in the upper left-hand corner some rags that are clogging the pump. I'm sure a lot of you have had to hand declog a pump before. Or you get things like these pipe aeration headers in the lower left-hand corner that are covered in rags, or the picture on the right, which is a clarifier that has been cleaned out of rags. About a once-a-week effect, trying to clean the clarifier out from rags, even though it's after a 1/4 inch or 6 millimeter bar screen that's supposedly a fine screen protecting it. So one of the things as we go through this presentation, you'll see the different types of screens being discussed. One of the big differentiators is it a one-dimensional screen or a bar screen, or a two-dimensional screen, or more commonly known as a perf screen. Bar screens with one dimension means you have can be a relatively fine slotted opening, but that slot can be very long and a lot of debris can make it through that slot. Rags and wipes tend to be one of the most common discussed pieces of debris coming into a plant, and one of the most harmful coming in. A rag very well may wrap around the bars or get placed across the bars and get pulled up by a rake, but it's also a very flexible item, could make it through those bars very easily. Whereas a perf screen is automatically going to be capturing the vast majority of those rags and wipes, as well as the other debris like tampon applicators and condoms and all the other unpleasantness that we deal with on a daily basis. That's much more likely to be caught by a two-dimensional screen. This is a quick demonstration that I frequently do. Used to do it at the engineering offices and plants that I visited up until they asked me to stop making a mess. But the idea being, this is a 6 millimeter bar over a 6 millimeter perf, or 1/4 inch for those of us here in America. You can see a lot of materials caught by that bar screen, which is why we commonly associate a 1/4 inch bar screen as being a fine screen, but a lot more materials caught by that perf screen. And that's really where one of the the common disconnects come in and where the independent testing is shown, there's a significant difference in capture rate. Now, when we start talking about the independent testing, one of the things that's going to come up is the different types of screens. The first is it a moving cleaning system or a moving filter media? You can break down every screen into being one of those two styles, where either you have a stationary bar screen or perforated plate screen that has a moving cleaning mechanism. Typically, that moving cleaning mechanism, as it passes by the media, can push material through that screen to end up with material getting downstream that you had originally caught. It tends to be a lower capture rate as a result, versus a moving filter media, where the media is in the channel and then being brought up out of the channel for cleaning, which means it has much less risk of material extrusion, but also typically a little more in the way of moving parts and cost. So depending upon what you're looking at for the plant, one of these may make more sense than the other. Of course, even if you have a good screen with all of the benefits that seem like they would give you a high capture rate, poor design can still make a difference as well. This is an example of a perforated plate style screen, typically one of the higher performing screens, but as you can see, this is the downstream side with a bar going across it that's capturing a lot of rags that are falling off of it. It's a function we call carryover. A poorly designed screen could still end up with a lot of that passing down, which is where you get pictures like this header I showed earlier, collecting full of rags. This is downstream of a quote unquote advanced style screen. So getting into the benefits of different style screens, how they're built, and the downsides is important, and that's where we get into third-party testing. Third-party testing has been done at the UK Weir National Screen Evaluation Facility. As you would assume, it's in the UK. They publish a report every few years. The most recent one was in 2015. That report is available for 35 British pounds, or about $40 to $42. You can purchase it electronically. That report has been very beneficial because when you're looking to evaluate screens, this is an independently done test. Manufacturers that are serious about testing or serious about capture rate will have their screens tested at this facility so they can have an independent report showing the performance out of that. The way this site works, they have an actual treatment plant in the UK. It's the Chester-le-Street plant. That plant has influent screw pumps that can be diverted to feed this test system, where they have flow monitoring, flow modulation, as well as the test tank itself. And then they run that as the headwork screening at this plant for however long they're going to be testing for. It's a multiple weeks long test. That test then is being done with the screen installed in the channel. They're collecting every bit of material that has been caught by the screen into a dumpster and weighing that. Downstream of the screen, the picture on the right-hand side, this is after the screen. They have a block-off plate that is going to have these media bags on them called copa sacks. They have a very fine mesh media on it. That means that any material that's been missed by the screen gets caught by these bags, and they can weigh that too. The end result of that is a simple ratio equation where you can look at the material caught Y over the material missed Z, and then get a SCR value, a screening's capture rate value, that is a percentage of all the material coming in. So a good screen is going to be a higher percent capture rate than a bad screen. On the low side with the capture rate, you can be at 30% range, but on the high side, you can be 90% or better. So this test is not necessarily intended to be pass or fail. It's not a digital result. You do have screens that perform better than others, but depending upon the application for the screen, a low capture rate may not be bad. It may be fit for that application. It's also not a perfect test protocol. It's not lab conditions. It is a real life, real plant, but they do run it over a long enough time period and under enough different conditions that it is getting a very reliable result out of it. This does produce a quantitative measure of screen performance effectiveness. So you're able to actually compare screens side by side, looking at the general screen types, the different ranges they have. As a result, it has been used globally to assist in screen selection. Frequently, the screen's capture rate value is a minimum number specified in the specification to ensure that a minimum quality is achieved for a screen. Now, there's a lot of different factors that impact your screening's capture rate. First, obviously, is the bar or hole. The Screen media makes a big factor. The opening size of the screen media makes a big factor. How is that debris handled? Once you capture the debris, how are you getting it to your container? Is it going to be carried up on a rake? Is it going to be conveyed with an auger? Is there any potential for that material to end up back in the downstream process? Additionally, sealing and tolerances. You can put a great screen in, but if everything can go right around the sides of it, it doesn't make a difference. So a good sealing system makes an important factor as well. Now, all of that can be undone by poor hydraulics. You don't have a good channel design where you have the ideal velocity through the channel and ideal velocity through the part or through the screen itself. You could end up with a bad, poorly performing screen. So all of these things need to be considered when you're designing a screen. During the UK Weir facility testing, they break the different screens into different classifications. There's the bar or slotted style screens, and then step screens, which were counted as a different category, but are still a bar style screen. And then what they call combined screens, which means there's an integral washer compactor with that screen style. Then they have fine screens, which were flow through style, as well as band style screens. The results, I've looked at all the 6mm only. They did test different sizes, but normalizing it across the 6mm or 1/4 inch, that's fairly industry standard accepted as a fine screen. You'll see that bar style screens got a 30 to 35% capture rate. Step screens also achieved a 30 to 35% capture rate. Combined style screens, they have an integral washer compactor, which is an area that you could lose material through. So these are going to be a different style, but these can consist of a screw screen, the stationary basket. Those got typically high 40s to mid 50% capture rates. Or it can be a rotating design where you have the screen media that's actually rotating out of the flow and getting caught that way. Those automatically got above a 60% capture rate. Moving to the flow-through style screens, these screens typically got in the mid to high 80% capture rates. Poorly designed screens did receive as low as a 70% capture rate design. They can be very finicky to get right. However, good screens of this style are actually the highest performing screens tested. The best performing 6mm opening screen has been the FSM filter screen at 85%. The center flow band screens, which are usually considered a very high performing screen, the highest number on that was 84%. Now, as you would expect, I was talking about 6mm opening sizes. They did test smaller opening sizes as well. The average performance for the capture rate did go up. You'll see most of these, when you get below that 3mm size, are exclusively MBR applications or more advanced process type applications, whereas 6mm is by far the most common for headworks protection. 3mm is kind of the no man's land, where if you want a little better protection than 6, you might go to 3mm. It's still typically too coarse for a more advanced process like an MBR. One of the end results from the UK Weir test is you get a certificate. The certificate, every manufacturer that is serious about screening capture has gotten testing done. They can provide you the certificate. That gives you the percent capture rate. The other thing that you can get out of the report that isn't given in the certificate is a written summary of how the screen performed. Was there any maintenance issues? Was there any wear and tear concerns? As well as hydraulic information available in the report as well. But at minimum, that screen's capture rate gives you a very good comparison in how the unit will perform overall. Now, screen channel design, you can take the best screen, put it into a poorly designed channel, and you'll end up with either a flooded channel or a lot of material getting downstream. So we need to make sure that we consider all the factors that go into screen design when we're looking at it. First is going to be the channel construction. Is there a certain width, depth, or length we need to constrain in, especially if it's existing? A retrofit can be much more challenging than a new channel construction where you can tweak it a little bit. The other thing is the application. Are we looking at just pump or screen protection? This is an area where maybe the screen's capture rate isn't so important. 30% capture rate is fine. So you're just looking to keep the logs and bicycles and things like that out of your pumps. Whereas, process protection, especially if it's an advanced process like an MBR, you're much more worried about capture rate. Then you've got your hydraulic gradients. Do you have a limit on the upstream water level? Are we going to be flooding your channel? Are we going to be flooding a basement upstream? Homeowners hate flooding basements. Similarly, do you have a downstream water level limitation? Typically, a screen wants as much downstream water level as possible, because that means more screen in the flow. The more screen in the flow, the more flow we can put through it. Lastly, channel and screen velocities. These are very important because usually we're arguing at opposites. On a channel, you want to have as much velocity as possible, because when channel velocity slows down, screenings are going to fall to the bottom, as well as grit will fall to the bottom of that channel. If that channel velocity doesn't pick up periodically and convey that down to the headworks, it stays in the channel, and then you need to manually clean it out. It's less than ideal, so we're usually aiming for a higher channel velocity. However, our screen velocity, we want to have relatively low. 5 feet per second is about the maximum velocity you want through a screen, ideally less than 4 if it's a bar screen. So we're aiming for somewhere in the middle on that. It does mean we're at odds trying to minimize one, maximize the other, but we can work within that. One of the important things to note is that if the channel width and the downstream water level are fixed, the only thing we can start to change at that point is this wetted screen area. So in a few slides, I'll be talking about ways we try to maximize that. But first, let's talk head loss. Head loss is frequently misconstrued when it comes to designing a headworks, because head loss through an orifice or through a pipe or something of that nature is very easy to calculate. It's a set amount of restriction. There's a set amount of driving head required to get a flow rate through it. It's very straightforward. The screen starts that way. With the downstream water level, that tells us how much of that screen is actually in the flow, how much of the screen is wetted, which gives us a certain surface area that we can work with. That means that we can calculate what's the driving head required to push that flow through the screen itself. However, if we assume that the screen is clean, that there's nothing blinding it, that means that during our peak event flows that we're typically sizing for, our peak flow through the plant itself, we need to run that screen all the time. The run time on a screen, the amount of hours you put on that screen, will decrease the overall time it is between rebuilds. So whereas a screen might last 5 or 10 years between a rebuild, if you're running it all the time, you might find you're rebuilding it every year, every other year. So the more time we can put on it where it's not running, where we're letting it build up a mat of material, the better. So usually what we're going to do is we're going to add some blinding effect so that we can account for not only the head loss through the screen itself, but a blinding effect. So typically you'll end up with up to 12 inches of head loss for that. We also build in a fudge factor. The more driving head we can put on it, the better. So that means that we're going to allow for even more. So typically you'll end up with a screen, the manufacturer will tell you that we want 15 to 18 inches of head loss. However, that will also depend on how much fudge factor is being put on it, how much runtime is being accounted for. All these will be important to consider when you're trying to estimate the best screen for the application. And then of course, one of the other variables is nobody knows exactly what's coming down the flow when. So asking how frequently the screen runs will really be kind of a immediate question back. What's your loading rate for the debris in the screen? So it's all important considerations, and it does complicate the head loss discussion quite a bit. Now, head loss is a function of velocity squared. What that means is that when your velocity through the screen doubles, your head loss increases by 4 times. So velocity through the screen is important. Velocity is simply a function of the flow rate over the area of the screen. So you can give me more area of the screen, a higher downstream water level, our velocity decreases, which means our head loss decreases. We have frequently, we'll be running scenarios where if we can double the downstream water level, our upstream water level actually stays the same, but the screen's going to work more effectively. So ultimately, why does screen velocity matter? It'll tell us what size screen we can get away with. How small of a screen can you use? Try to keep costs down, try to keep channel size down, but this is what we're trying to calculate off of, is your ultimate velocity. Now, the head loss, the velocity, that area, that's partially based on the open area of the screen media itself. So you've got a bar screen or a perforated screen, you're putting a certain amount of metal into the channel that's then going to be trying to capture as much of that debris as possible. So the debris is actually not resting on the metal. That means that you've got blocked off flow, the areas water's not going through. The open area, the smaller the opening is, the less open area you'll have. So, that's one of the considerations when you're trying to calculate your hydraulics is how tight of a screen can you go with. We're continuing to try to push the edge on that. Recently, we've been able to improve on the perforated opening area size from 51% for 6mm to above 60%, and from low to mid 40s for 3mm up above 50%, which is going to give you a significant increase in flow capacity. But outside of that, the only ways you can really increase your velocity is start to change the water level in the channel itself or the screen opening area. A quick thought experiment, visual thought experiment on how this velocity impacts us. I've got an example here, 3-foot wide channel, 2 feet deep, using 4.5 MGD as my flow rate, which works out to 7 cubic feet per second. Trying to make my math easy and avoid trigonometry here. So we're assuming a 90-degree screen with that 3-foot wide channel, 2 foot deep at 7 cubic feet per second. Your velocity in the channel is 1.2 feet per second. Now, as soon as you put in your screen into the channel, you're going to have side seals and you're going to have frames and whatever else in that flow. So now you're decreasing the area that flow is going through. So we've already increased our velocity through the screen to 1.8 feet per second. Now we've got that open area where you've got bars or perforated plate that's in the middle of the flow. At a 6mm opening, you're around 50%. Bars are 45, 48%. 6mm could be 51 to 60% perforated. Now your velocity through the screen is increased to 3.5 feet per second. If you account for some blinding factor on that, 30% is fairly standard. Now you're up to 5 feet per second through the screen. If you recall, 5 feet per second is the maximum flow rate that we ideally put through the screen, but our channel velocity is still only 1.2 feet per second. So, we need to try to maximize that and improve on it so that we can keep our velocity through the screen at 5 feet per second or less, but try to make sure that we do hit that 1.2 feet per second velocity a few times a day. So one of the first things we do, I assumed calculations for the 90-degree screen because, again, avoid trigonometry. But if you do start to use a screen that has a shallower angle on it, now you're putting more wetted area into it for the same given downstream water level. That means that you're going to decrease the velocity through the screen, decreasing your head loss, or allowing you to increase the flow capacity for the same given head loss. The downside being the shallower the screen gets, the more surface area it takes up. You go to an extreme impact, looking at a in-channel drum screen or screw screen, that can be a 35-degree angle, which you can imagine takes up quite a bit of room. One of the ways we can get around that is going to a multi-angle style screen. This multi-angle screen means that you can have a significant reduction on the head or an increase in the flow rate going through. Because you're at a 30-degree screen in the shallow section, but a 75-degree screen in the steep section, which is going to take up about the same amount of space that a 50 or 60-degree screen might take up. So it's a significant reduction in space take up, but gives you a much higher flow rate capacity through it. Now, one of the unique things, that the downside to a in-channel drum or screw screen is that 35-degree angle. So it doesn't work very well in deep channels, but because it has that basket style shape to it, when you have low flows, you've got a relatively low amount of the basket utilized. As water level rises, you're exponentially increasing the surface area versus a straight screen where you're linearly increasing it. So these screens for shallow channels are a great way to try to minimize your head loss through a screen. Now, choosing the right screen can be difficult. There's a lot of options out there, but one of the benefits is, we've got some questions we can ask to help narrow it down. The first is, what's your flow range expected? If you have a relatively low flow range where you're looking at, say, less than 3 MGD peak flow and, half an MGD, 1 MGD average flow, there's a lot of screen options out there, but, chances are you'll be looking at a screw screen or in-channel drum screen or something like that. You get into the bigger flows, that starts knocking those out. Now we're looking at more of a bar screen, perf plate screen, what have you. The performance goals are going to be an important factor. I'm joking a little bit here about, do you want wipes in your plant? Bars are how you get wipes, but in all reality, if you're looking to have a good performing treatment plant and you're looking to protect your processes downstream, perforated plate screens are going to be a higher capture rate. So that's one of the factors you're looking at is, where do you want to make your compromises in your purchasing versus your maintenance? Then hydraulic restrictions. Do you have a upstream or downstream water level that you have to contend with that's fixed? And then will be a new construction or retrofit. Retrofit does add some additional complexity to it, but is certainly something that can be accommodated. A quick comparison, Multirake bar screen, proven 30-35% capture rate. It's also a robust, proven technology. It's been in use for a long time. There's a lot of installations out there. It's a well-known design. Perforated plate flow-through screens, though, are also a robust, proven technology. They've been around since the 80s. They've been continually improved on ever since. They can also get up to an 85% capture rate. Consider on average, a perf plate screen is going to be 5 to 10% more than a multi-rake screen, but it's going to capture 2.5 times the material. And a lot of that material is going to be the rags and wipes that are causing issues downstream. We see a lot of plants, so when they go from a bar screen to a perf plate screen, all of a sudden don't have clarifier failures after storms, they don't have pumps plugging up. It's a lot of cost savings long term. So I'll be spending some time here talking about different screen types. I'm going to focus primarily on multiple rake style screens, incline drum screens, perforated flow through screens, and center flow screens. Put an asterisk on the center flow screens. They're more of a specialty style screen for raw water intake and membrane protection, but do have some limited applications in headworks as well. So the first thing is, what is the peak plant flow range? Typically, plants are sized based on the average flows for their processes downstream, but for the headworks, we need to know what the peak flow is, because ultimately we're sizing to make sure we're not, going to be putting flow out of the channel or causing other issues. So we're going to size on that peak flow rate that you want per screen. The incline drum screen is going to be the one that's best for your smallest flows. You can handle a flow of up to 20 MGD plus in that, but its sweet spot's really anything above 3, 4, 5 MGD up to about 10, 15, maybe up to 20. Multi-rake screen can handle larger flows, especially when you're getting into porch protection. It can handle very large flows. The downside being, compared to a flow-through screen, which can handle similar flows to multi-rake, doesn't have the same capture rate. Channel depth is one of the other considerations. Incline drum screen, it's very effective for channel depths up to about 10 feet. The multi-rake screen is going to be much more suited for deeper applications. You'll see here it's showing an average of up to about 50 MGD, or 50 feet, but we have installations as deep as 180 feet as well. It can be a very flexible screen for going deep. The flow-through screen, given that it has a whole panel of belts, whole belt of panels on it, that flow-through screen is going to be a little less deep. We can still go 30 plus feet on it. We have some installations up to 50 feet on it, but that one is a little more limited on depth. The installation angles, you'll see the incline drum screen is only installed at 35-degree angles. Limited applications, it can go down to a 30-degree angle, but it's typically 35 degrees. Multi-rake screens can go as steep as a 90-degree angle. That gives you a very small footprint take up, but also hydraulic impacts on that. Most installations are a 75-degree angle. The flow-through style screens can be as shallow as a 30-degree angle, typically around that 60 to 80-degree range, with the majority of them at 75 degrees. So moving into what these screens actually are, I've talked a bit about their applications, their performances, but how do these things work? Well, I'll get into the multi-rake here. It's an excellent porch protection screen. You'll see that there's a bar field down in the bottom that's going to be in the flow itself. The flow is going from the left to right here. You'll have a chain that rotates around counterclockwise with rakes periodically on them to clean the bars. So as the rake comes around, you'll be picking up debris from the bars, bringing it up to the top where a wiper is going to wipe it off. And then the material is going to be dropped down into a screenings dumpster, conveyor, or washer compactor. Down at the bottom, there's typically some sort of fixed guide that's going to be either stationary or revolving. That's going to be a way that you're keeping the chain down, forcing it to engage the rake directly into the bar field, and then pick up any material to bring it up and out from there. A lot of these designs are interchangeable. You can either use a stationary guide or a revolving guide on bolt one, bolt the other end. You'll find frequently the revolving guide is recommended. This has less drag. It's a more secure engagement to ensure that it's properly tracking, no side-to-side movement. Obviously, it's one more moving part down in the channel, so the stationary guide does have its benefits there. The other thing is some of these you'll have no guide down the bottom at all, no fixing pin design, frequently referred to in the industry as a flex rake style. The benefit of those is that here you're permanently engaging that rake into the bar. If something large comes through and that rake tries to engage it, it will get stuck. It'll have to back up and go through a jam logic sequence to try to move it out. These flex rake styles literally climb over them, pushing the rakes away from the bars to bring the material up. It makes for great course protection because you pull up, large logs, tires, things of that nature. It also means that during that time period, it's not engaging with the bar, so you're not getting any cleaning effect. So what are some common applications for these? Best applications for multi-rake is funk protection, as well as pre-screening applications. MBRs being one of the most common ones, where you're putting in the screen, then doing grit removal, then doing a secondary screen for the actual MBR protection. So this is a staged screening application. It's great for these. One of the big advantages is very robust, very low maintenance. Disadvantages, low capture rate. Raw water applications is very similar. It's a good course intake screen. It can handle a lot of debris. It's not going to be broken by logs, rocks, and other debris like that. If you go with the unpinned style, it'll even do better at removing that. Disadvantages, if you don't have the unpinned style, then it's not going to be able to convey some of those larger debris up and out. It also has a lower capture rate than some of the other raw water style screens, like a traveling water screen or a center flow style screen. Moving on to the perforated belt screen details. These screens have been around for a while. They've been slowly taking over the market for headworks protection because the focus has become more and more on fine screening, trying to get the rags and wipes out. You see, it was developed way back in '86. It has been continually improved on ever since. In 2013, it achieved the highest capture rate for a 6mm screen ever tested at the UK Weir facility at 85%. It's continued to be improved on ever since with auto brush developments, as well as that multi-angle style screen. You'll see in profile, it looks very similar to a multi-rake style unit. You've got a side frame with two rotating guides on it, and then a chain going around. The difference being, instead of periodic rakes connecting the chain, here we have perforated plates connecting that chain instead. These perforated plates, you'll see, typically are rounded with lifting fingers located on them. As the flow is coming again from the left to the right here, you'll build up a mat of material, and then as that mat gets built up, it'll turn on, bring the belt around, where it'll get cleaned up the top by a cleaning brush. It's rotating counterclockwise to the opposite of the belt, and then material gets dropped down to the bottom, again to a wash press, a conveyor, or a dumpster. Typically, these also have a water spray. Sometimes they only have a water spray. A well-designed screen is going to be using the majority of the cleaning being done with the brush. The backside water spray then would be used for a bioslime buildup. Does not need to run all the time. You're going to rely on the brush with a well-designed screen, but you do periodically get bioslime on the backside. The water spray helps keep clear. Now, this is what the screen looks like in the front of the channel. So you can see you've got a complete covering of panels in the front. They're tightly connected to each other, so you don't get any flow going in between them. That's part of that sealing effect that's very important. You also see there's side seals and lower seals to make sure that nothing is able to bypass. These panel designs, they've evolved over the years. The initial panel design introduced by FSM when they introduced technology had a ledge to it. The idea being, sticks and stones and other debris that doesn't literally stick to the perf panels will then sit on those ledges, be brought up and removed that way. What they found was, A, it's not very effective at removing that because you have to wait until that panels come all the way around to actually have it rest on the ledge to bring it up. But it also makes it very hard to clean inside this crevice in here. So you get a lot of debris that would sit in there until it comes around, and then the force of the water going through the channel brings it out, which then creates a condition called carryover, where you could lose that material that you've caught once, carried it over, and then let it go downstream. It's not very ideal. So this is where the panel design has been improved. Go to a curve style design. One of the big advantages of the curve style design is as the panels come up and around, you have a sprocket in here. The curvature matches the sprocket so that the brush is in constant contact with the same point on the panel all the way around the cleaning point. Even the inside of the knuckles starts to open up for cleaning inside there. Makes for a very effective cleaning mechanism, and then the spray bar on the backside is being only used for the bioslime buildup. You can see here the difference. The original design, the older designs, having a brush down at the bottom, you can only effectively really clean the top of the panel, or you can put more pressure on that brush, adjust the brush in further. You might do a better job at cleaning the panel, but now you're going to start to wear both the brush and the panel much more quickly. So with a proper brush location, you get a much more effective cleaning on the backside of that panel. Now, brush wear is a concern with this style screen. It is something that is important to keep in consideration. Typically, you'd be adjusting the brush once every month or two to keep it in proper contact with the panels. With newer systems, you'll have an automatic adjusting brush. That brush means that there's no adjustment required until that brush needs to be replaced. It's also increased the lifespan of that brush. Older systems typically have every 2 to 3 years, if not sooner, you're replacing the brushes. On newer systems, they're lasting 5 years or longer because now that brush is always in the proper adjustment all the time. Bit more zoomed up video of it for you guys doing remotely. Now moving on to incline drum screens. These are also perforated style screen, very high capture rate. The big variable on these is that drum size. You can have anywhere from a 2-foot diameter drum, a little baby drum, up to a nearly 10-foot diameter drum. So these can be used for a wide range of flows, from very small plants to very large plants. They can be installed in a channel or they can be installed in a tank. They have a very high capture efficiency because of the perf blade design and the design of the drum screen itself and the cleaning mechanisms. Makes them very popular for MBR designs as well as regular headworks applications. They say a picture is worth 1,000 words. Video's got to be worth a little more. This video is going to show that the screen flows coming from the left to the right. You'll have a block-off plate in that channel that's forcing all the flow into the middle of the drum. As material gets caught on the drum, it's going to rotate up, get cleaned by a spray bar at the top, pushing all the debris into a conveying trough. That auger is located in a trough. It's currently invisible. You'll see the auger is driving the drum rotation as well. They are interconnected, which means there's only one drive total on this system. As that drum turns, the spray bar drops everything into the trough. That trough then brings the material up and out with that auger system. You'll have additional spray points as the material gets brought up and out. And at the very top, there will be a compaction zone that's taking all that captured material, squeezing it, additional cleaning going on, and then taking all the water that's cleaned out of it and bringing it back down into the channel so that you've got only the water material coming out. And that can go either straight into a dumpster or that can go into a conveyor system as they show here. It's a very simple unit, and one of the main benefits being everything is integral to the unit, including the compaction zone. So it makes it much more cost effective, especially for smaller plants. So common applications for this, first of all, it does make a good headwork screen. It's very low maintenance. While it does have that big drum turning, that's about the only turning item on it, the drum and that auger. There's a couple locating roller supports, but otherwise there's very little moving parts. It makes it very low maintenance overall. It does have a very high capture rate, especially considering it's one of the combined screens. It also makes for very good NBR applications, post grit removal, doing 1, 1.5, up to 3 millimeter screenings on it. It's also common for sludge screenings in the 3 or 6 millimeter opening sizes. This can be either a tank unit that you're pumping up from your sludge screens or your clarifiers, or it can be in a channel located after the clarifiers as well. Moving on to the center flow screen. This is an excellent water intake or MBR screen. The way these screens work, you can see there's the screen down in the channel. Flow is going to come in, turn 90 degrees going through it. So you've got this throat that's going to be taking the flow in. One of the concerns with these styles is that they have a fairly complex hydraulics regime through it. There have been issues with these screens in the past meeting the hydraulics requirements, so they can be very touchy to get right. But as the flow goes through that throat, that makes that 90-degree turn. The water level you'll see in here is variable depending upon the flow rate going through it, and that will change your wetted area there. One of the considerations as well is this flow comes in here, makes the turn, you can get a lot of grit deposition down at the bottom. So usually what you'll have is a opening in the backside that allows you to periodically open it and flush the flow through and keep the grit moving. It's an important part of the maintenance on this, because otherwise, as this belt comes around, it'll keep driving through the grit collected down at the bottom. So typically, these have been used for clean water applications. They also started being used for MBR applications after grit removal for all the reasons discussed earlier, because it does have a very high capture rate, especially when you get down to the smaller opening sizes. You can see a 90% or better capture rate out of this style screen. So it's very common for MBRs. Once it started being used in wastewater applications, the next question was, do you want to move it upstream and have it be a course protection screen as well? The primary downside to this is a course protection screen, is any larger debris that comes into this has to be able to be lifted up by those lifting fingers that are used to pick up the debris and deposit it. Anything larger, picture a bowling ball, for example, but any debris of that nature could work. As that comes in, the lifting fingers will try to lift it up, it'll fall back down, and then it will land directly on these panels. You'll see a lot of these style screens end up with dented or broken panels as a result when they're used for course screening protection. So while they can be used for course screening protection, it's not a recommended application when you have some of the other options available that would be better suited. They do have a couple different basket styles, especially when you're looking at raw water treatment. Typical wastewater, you'll have just the flat screen. Raw water intake, you might have fish buckets added in, or it might even be a complete basket style screen instead of the fish buckets. If it is a raw water intake, usually you'll have two collection troughs, one for the fish to fall into, and then another one for the actual screening debris to fall into. So getting into the screening summary on this, I'm going to talk about a quick summary of each of the four. First being the multiple rake, second being the incline screw, then perforated plate, and then center flow. So the primary advantages of your multiple rake screen is it's a fast cleaning screen due to those multiple rakes. You can run the chain quickly, you can have a lot of rakes on it, so it's always cleaning that bar screen off. It's very good for deep channels. As I mentioned earlier, we've got installations as deep as 180 feet, so this can be a very good deep channel application. It's also very good for protecting pumps because it can pull the large debris out. It's also good for gravity flow sewers where you have a lot of large debris, picture the bicycles, Volkswagens and stuff that can go through some of these large sewers and end up down at the pump station. Also great for remote applications. There's no wash water needed with this style. Most screens are going to require some form of wash water. This style screen does not require one, so it's good for remote pump stations where you don't have a lot of wash water available. Of course, the downside, I hope at this point I've made it very clear. It's a bar screen, slotted opening. It's going to have a very low capture rate as a result. Now, a perforated plate screen is the opposite. It has a very high capture rate. It's one of the main advantages it has. It can also fit into a deeper channel. We're not going to do 180 feet deep with it. 50 feet is certainly an option. And because it can be installed up to an 80-degree angle, it's not going to take up a lot of room for those deep channels. So it's a very good fit for a lot of applications like that. It's excellent for protecting actual processes downstream, not just pumps or things of that nature, but getting into your clarifiers and digesters and everything else. Makes for great protection, much reduced downstream maintenance costs as a result. It's also very good for gravity sewers because of the way it's designed with the strong panels. A lot of these screens are good at handling gravity sewers. They can take a bowling ball coming down, they can take logs and stuff coming down. So some of these I may not be able to remove, but at least it's not going to be landing on top of it like a center flow would. It's also very comparably priced to a multi-rake, so it's relatively inexpensive for a good fit. And because it has new panels always being introduced as it's running, it has a very fast cleaning cycle. Now the disadvantages, it does require a screenings compactor because you're pulling out so much in the way of screenings. A lot of debris will land on the outside of it. It needs to be washed and dewatered because you get a lot of water pulling out. At minimum, a conveyor compactor would be recommended, if not a full-on wash unit. It also does have some carryover potential if you don't have a good cleaning system on it. We would recommend looking for something that has an automatic brush on it so that it's always in contact and you're always getting a good cleaning system. In-channel drum screens. These in-channel drum screens are going to provide a very good capture rate. They're a very cost-effective solution for smaller flows because they do have a internal compaction zone on them, internal compactor. They're also very proven NBR protection at the smaller opening sizes because they're no carryover design. Primary downside, not so good for deep channels. Channel widening may be required to get into these big wide screens. They'll be typically wider than the channels themselves you're trying to convey the flow in. It does have a limitation on the upstream water level. In the picture, you don't want the water level to go above this, otherwise it'll bypass. It's also not great for gravity sewers because while it can typically handle some debris getting in, it can't handle conveying them up and out due to the auger size. Then lastly, the center flow screen, very long water treatment history, growing wastewater treatment industry, but primarily for the MBR style screens, does have a good no carryover design that results in a high capture rate. But because of its vertical orientation, not as recommended for wastewater core screening. It does have some difficult hydraulics. You want to make sure you get those right so you don't have issues upstream. Not terribly suitable for gravity sewers simply because if you are using it as a core screen, gravity sewers are going to have the potential of debris landing on here and not being able to be pulled up and out. So what did we learn today? For effective plant protection, perforated plates are going to make a big difference. If you're looking at a headwork screen, you're looking to protect your plant, a perforated plate is going to be 2 to 3 times the capture rate that a bar screen is going to be. It's also going to be very little price difference between a bar screen, so it's going to be ultimately, the no-brainer for most applications. Not all, but most. UK wear testing is a great equalizer. It's a way that you can be baselining the equipment to compare different manufacturers and different styles of equipment. You'll find very little differences sometimes can make a big difference in the capture and operation efficiency of that screen. And then, of course, hydraulics. Screen design is not simple. It requires a lot of different considerations when you're looking at how to best operate that screen. That includes your wetted area, getting into that head loss, what is the head loss, what is allowable, and ultimately, how frequently do you want that screen to run? And then your channel velocities. You want to make sure your channels themselves are working properly. So thank you for your time. If you have any questions, I am happy to answer them. My contact information is available here. Thank you very much. Have a great day.